Okay, my name is Yanofsky. We're doing analysis of algorithms. We're up to chapter 15, Dynamical Programming. So let me tell you what dynamical programming is. Dynamical programming is basically recursion upside down. Okay, now let me just say, why is it important? Well, it's just as important as recursion, and as we saw, recursion shows up all over. Okay. What do I mean by upside down? First, so let's just remember what recursion is. Recursion is you want to solve a big problem, so here's what you do. You solve the small problems first. You call the program to solve the small problems first, and then you unite all the small problems and you bring it together. Dynamical programming is very, very similar to that. Okay? You solve the small problems first, but instead of calling yourself, you save the information first. You save the information of solving the small subproblems first, and then you bring them together. Let me show you an example. So the simplest example of recursion, the one that you saw in the first semester programming, is factorial. So let's just remember what it is. 1 factorial is 1, n factorial is n times factorial times n minus 1. Okay, so if I ask you what, let's go usual notation, 7 factorial, well that's equal to 7 times 6 factorial. Okay, great, but what's 6 factorial? That's equal to 7 times 6 times 5 factorial. Okay, what's 5 factorial? What's 5 factorial? 5 factorial is okay, and this goes to 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, great. So the main point is, in order to figure out n factorial, we have to call and solve first what n minus 1 factorial is. Okay, that's recursion. That we saw from the first semester. Okay, but let's talk about the dynamical way of programming it. Okay, the dynamical way of programming is much easier. It says as follows. You want to know what 7 factorial is? Very simple. Figure out what the small problems are first and build up till you get to 7. So 1 factorial of 1, so this is going to be a matrix called factorial. Factorial of 1 is 1. 1 times 2 is 2. 2 times 3 is 6. 6 times 4 is 24. 24 times 5, I'm reaching my limited ability. 5 times 20 is 120. Oops, is 120. Times 6 is 720, etc., etc. Etc., etc. means I have no idea what 7 factorial is. Okay, anyways, that's the way you do it. You build it up from the small problems. You build it up from the small parts first. Okay, let's just do Fibonacci's. Okay, again, that's probably done in first semester recursion theory. Recursion is the first example of recursion that you see. Okay, the Fibonacci of 1 is 1, Fibonacci of 2 is 1, Fibonacci of n is equal to Fibonacci of n minus 1 plus n minus 2. Okay, great. So how do we figure out the 13th Fibonacci number? Well, you'd have to figure out, in order to figure out the 13th, you have to figure out the 12th and the 11th. In order to figure out the 12th, you have to figure out the 11th and 10th, etc., etc. Okay? But rather than do that, all you have to do really is just figure out the small ones and build up to the larger ones. 1, that's 1, that's 1, and 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 21. 13 plus 21 is 13 plus 21 is 34, etc., etc. Okay, so you're going to know what the final answer is over there. Okay, so that's what we're going to do. We're going to have a problem. It's going to be a complicated problem. We're going to build up the small solutions first, and then we'll go to the larger solutions. Okay. There are 5 sections of this chapter, and I want to just give you an outline of what we're doing and what you're not. Okay, section 15.1 is rod cutting. It's a nice example, okay, but it's a little bit, it's 10 pages to get into the example, and we have enough other examples. Okay, so we're not responsible for that, and I didn't give you homework for that. In contrast, section 15.2 is matrix chain multiplication, and that we're going to do today. And it's a beautiful example of showing how this works. Okay, section 15.3 is like a little bit of a philosophy. It's called Elements of Dynamical Programming. Okay, it's like explaining what it's all about. It's kind of what I just said already, but we're not responsible for it, so we're not going to do that. Now, section 15.4 is called Longest Common Subsequence. And that's as follows, and we will do this. Given two strings, find a sequence that fits into both of them. But it doesn't have to be continuous. You'll see, but it's a beautiful thing. We're going to do that. So we're going to do this, we're going to do that. And finally, the last one is section 15.5, okay? And that's called an optimal binary tree. So binary search tree. Okay, so let me just tell you what that's about. We saw at the end of binary trees that it could be that binary trees will not be pretty. In other words, they'll be long. Well, we would like a way, and again, what does it mean for a binary tree to be pretty? It means it's short. Well, we'll see a certain way to make it as short as possible. Okay, so we're going to do these three sections. Okay, very nice. We're going to do these three sections. I just want to point out, it's a beautiful subject. Okay, it's an absolutely beautiful subject, and it's easy. It's not hard to do. But I want to show you that in this booklet I gave you, the first thing, I took from another book, Sarah Bassey's book, called Introduction to Algorithms. It's a very nice book, but it's we're not using it. Okay, and I gave you their entire chapter on dynamical programming. Okay, and look, they do the same thing as we do: matrix multiplication and optimal binary search trees. So matrix multiplication and optimal binary search trees. So you're going to see it another place besides this. Okay, let me just show you, and we're going to come back to this because I'm going to go through some of their examples. They also do other things in matrix multiplication, and we will do it too. Distances and graphs. They do other types of dynamical programming exercises. It's a little bit easier to read, but I really think that once you listen to the lecture, look at this, you should be able to get to Corman-Lies and Rivest's book. Okay, so we're going to be doing it in both. Okay, great. So let's start with section 15.2, matrix chain multiplication. Okay, and it's a very pretty example. Okay, so it goes as follows. Section 15.2. Okay, matrix chain multiplication. Okay, and it goes as follows. Let's say you have two matrices. We did this the first day of class where we talked about n squared when you have two n by n matrices. But let's say you don't have two n by n matrices. Let's say you have different size matrices. So, for example, you can have a 5 by 8 matrix, okay, and that can be multiplied by an 8 by 3 matrix. And what are you going to get out of that? Well, you're going to get out, notice these numbers have to be the same, and you're going to get out a 5 by 3 matrix. Okay, great. that we knew the first day of class. Well, but the question is as follows. How many operations does it take to get this? Well, let's go through it. You have 5, this is 5 rows by 3 boxes, so you have 15 boxes to fill in. And each one of those 15 boxes, in order to get them, you have to take this row, that column, and this row, and you fly over and you multiply each one out. So you're going to have to do, for 15 boxes, you're going to have to do 8 multiplications each. Okay? And so conclusion, this is going to be to multiply a 5 by 8 matrix by an 8 by 3 matrix is 15 times it, or 5 times 3, okay? But also, you're going to have to multiply each one of these squares that you have to fill in, each one of the 5 by 3 squares, you're going to have to fill in, you're going to have to multiply by 8. Okay? So just keep this main thing in mind. When you have a 5 by 8 and an 8 by 3, you have to do 5 times 8 times 3 operations, multiplications. Okay? Let's just do it in general. In general, if you have an m by n matrix and you have an n by p matrix, then you're going to get out an n by p matrix, an m by p matrix. Okay, you're going to get out an m by p matrix, and each one of those m by p things, you're going to have to do n operations. You're going to have to multiply the n elements of this column by the n elements of that thing. Okay, and so altogether you're going to have to do m by n by p multiplications. Keep that in mind. You'll see why it's important in a second. Great. Now, question. So we now know how many operations it takes to multiply two matrices. Question. How many operations does it take to multiply 3? So let's work it out. So let's do a nice example. Let's take 3 matrices. An 8 by 3 matrix, a 3 by 2 matrix, and a 2 by 1 matrix. Now, all 3 of these can be multiplied out. This shares a common number, and this shares a common number, so they can be multiplied out. Okay, so how many operations does it take? Let's think about it. Okay, well, to multiply these 2 matrices, by the way, how do you multiply matrices? 2 at a time, just like how do you multiply numbers? 2 at a time. So let's multiply these matrices. In order to multiply an 8 by 3 and a 3 by 2, you need 8 times 3 is 24 times 2 is 48 operations. Okay, but what are you going to get out of this when you finish? You're going to get an 8 by 2 matrix, and here you have a 2 by 1 matrix. Okay, so when you multiply these out, you're going to get an 8 times 2 times 1 is 8 times 2 times 1 is 16 operations. Okay, so let's count up how many operations you did altogether. 48 plus 16. 48 to bring these 2 together, 16 to bring these 2 together, and you get 64 operations. By the way, when you finish, you're going to get an 8 by 1 matrix. Okay. You're going to get an 8 by 1 matrix. And you did it in 64 operations. Question, can you do better? And the answer is, let's see. You see, because there's another thing you could do also. 8 times 3, 3 times 2, 2 times 1. You could do something else also. You can multiply these 2. Matrix multiplication is associative. Associative means it doesn't matter where you put the parentheses, you're going to get the same answer. But let's see how many operations it takes to get the right answer. 3 times 2 times 1 is 3 times 2 is 6, so this is going to be 6 operations. 6 operations. Okay? And then you're going to get out of this a 3 by 1 matrix. And then you're going to have an 8 by 3 matrix and a 3 by 1 matrix. In order to get that, 8 times 3 is 24 times 1 is 24. So this is going to be, to get this out, you're going to get 24 operations. Okay, and at the end, you're going to get, just like over here, an 8 by 1 matrix. Not only are you going to get the same size matrices, but again, because matrix multiplication is associative, you get out the same answers. In other words, the 8 numbers here and the 8 numbers here are going to be the exact same numbers in the same order. You're going to get out the same array. Okay, great. Question, how many operations is this? Well, 6 plus 24 is 30. You'd rather do 30 operations than 64 operations. Okay. And of course, we're dealing with small numbers here. You'll see why this is relevant when we're dealing with larger numbers in a few minutes. Okay, great. Okay, so that answers for 3 matrices. Now, I could put in numbers into these things where it would be better to multiply these 2 first rather than these 2 first. It's not clear which ones to do first. It depends on the sizes of your matrices. Great. Let's go on. Let's talk about, now that we saw a way of solving 3 matrices, how about solving 4 matrices? In other words, when you have 3 matrices, there are 2 ways of doing it. How about when you have 4 matrices? Okay, so let's say you have 4 matrices, A, B, C, and D. How many different ways are there of parenthesizing or associating 4 matrices? Stop the camera, try to figure it out yourself, try to do it yourself. Figure out how many different ways there are of doing it. Anyways, we'll do it. You ready? A, B, C, D. You could do it like that. Or you could do it like this, A, B, C, D. Or you could do it like these. Or you could do it like this. Or you could do it like this. Okay? There are 5 different ways. 1, 2, 3, 4, 5. 5 different ways of associating 4 matrices. Which way should you do it? Okay. 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 And we're going to figure that out. We're going to put in values for A. And we're going to put in, not values, but dimensions. What are the dimensions of A? What are the dimensions of B? What are the dimensions of C? What are the dimensions of D? And it will tell us what's the best way of doing it. Very good. Question, how about if I give you 5 matrices? Okay. How many different ways are there of doing it? Of associating them? Okay. You can sit down and try to work it out. Okay, how many different ways? Well, I can put parentheses around here, then around here, then around here, then around here. I can put you can try it, and it's actually worth doing it. Take a piece of paper and try it. Okay, it turns out that there are 14 ways of doing that. There's 5 ways of associating 4 elements. There's 14 ways of associating 5 elements, and something like 72 or 62 to associate higher. 132 to associate 6 matrices. Okay, I'm not making this up. This these numbers are called the Catalan numbers. Okay, and the formula is as follows: 2n choose n divided by n plus 1. And you can look up in the Wikipedia page. There's millions of examples of where this formula shows up. Not millions, whatever, but many, many times, many different ways that this formula shows up. So it's a very important formula. We're not going to deal with it. Okay? We're just going to deal with, but now we can ask the general question. Here's the general question. If you have n matrices, in what way should I multiply them out? In which associativity should I use to multiply them out so that I can get the least amount of operations? That's the general question. Okay? And we're going to do a nice example and see how we do it. Okay? let me just motivate first a little bit. If you work in an engineering firm or an architecture firm, you're going to get giant 500 by 500 matrices, 400 by 500 matrices, and you're going to have to multiply them out. Okay, so dealing with 8 by 3 matrices and 6 by 2 matrices, it doesn't really make a difference. But when you get into big numbers and you have to multiply, let's say, 50 different matrices, one after the other, you get into some heavy numbers. I told you this the first day of class. I said as follows: if you want an easy way to test your computer with a 5-line program, you can randomly pick a matrix, okay, with random entries, okay, randomly pick a matrix with random entries and multiply it by itself, 500 by 500, 500 by 500 matrix by itself, and you get, again, matrix multiplication is an n to the cube thing, okay, matrix multiplication is an n to the cube thing, but if you do matrix multiplication by itself 500 times, that's another outer, what's that word called, loop outside, okay, and so that's an n to the 4th operation. N to the 4th operation with n is equal to 500, you get really big numbers. Okay, so it makes a difference, but that doesn't really make a difference because you're always multiplying the same thing over and over, so it doesn't matter really how you're doing it. But this problem really shows up when you have different dimensions of things coming and going. Okay, so let's deal with that. Okay, so that's one thing. Okay, we're going to talk a more general, so let me just do this general problem. The general problem is as follows. You're given matrices A1, A2, A3, A4, till an minus 1, A of n. You're given n different matrices, and you want to know, I need to multiply them all out and get 1. I'm assuming that they can all be multiplied out in the sense that their dimensions are correct. Okay, and so I have to ask the following question: which way should I multiply them out so that I can get the best? Okay, in other words, the nth Catalan, there are n Catalan numbers, the nth Catalan numbers of different ways of multiplying them out. I want to know which one I should do to have the minimal number of operations. Let's just make it a little bit more, we're going to need it for recursion. Okay, I am asking the following question. I want to multiply, I'm given the n matrices, but I want to multiply just AI plus 1, AI plus 2, AJ minus 2, AJ minus 1, AJ. I'm given these matrices, I'd like to know what's the best way of multiplying these. Given all these things, I just want to solve a sub-problem of that. I want to multiply from I till j. What's the best way of putting parentheses around it? Okay, so that's what it's all about. Okay, great. Let me show you an example, and we'll work it out together. Okay, the book has slightly strange notation about this, and let's do that. Okay, so this is the strange notation of the book. They, for some odd reason, they have the matrix sideways. Okay, and so this is the matrix M. There's another matrix, and I'll explain to you what that matrix is also. The book also has that. And basically it's as follows. M of ij is equal to, where this is I and this is j, is equal to the least number of operations to multiply AI through AJ. In other words, they're keeping count of what's the least amount of operations you need. Okay, so that's what it's all about. Okay, so here's a nice example. It's not from the book. The book does a beautiful example with 6 matrices. We're going to do a beautiful example with 4 matrices. So you have a 5 by 10 matrix, a 10 by 13 matrix, a 13 by 7 matrix, and a 7 by 10 matrix. You notice each one of them can be multiplied by the other one, okay, by the next one. 10, then 10, 13 and 13, 7 and 7, so they match, so you can multiply them. Okay, and the question is how many operations, how many operations you need. Okay, great. The first thing to do is to get these numbers, 1 to 2. What's 1 to 2? So how do you multiply the first matrix times the second matrix? Answer, 1 to 2 is 5 by 10 and a 10 by 13, which I showed you before is 5 times 10 by 13 times 13, which is 650 operations. Great. The next one is 2 to 3. How many operations do you need to multiply a 10 by 13 and a 13 by 7? And the answer is 10 times 13 times 7, which I worked out to be 910. Great. Next, 3 to 4. How many operations do you need to multiply 3 by 4? So 13 by 7, 7 by 12. I told you that's 13 times 7 times 12. That's 1092. Very nice. Okay, so that takes care of the bottom thing. Our goal in life is the top thing, from 1 to 4. We want to know how to multiply 1 to 4 from the beginning to the end. What we're doing now is we're solving the small problems first, and then we're going up to the large problem. Again, I told you, dynamical programming stores the results of the small problems in a matrix. But in Fibonacci and factorial, the matrix was a one-dimensional matrix. Here the matrix is going to be a two-dimensional matrix. The rest of our examples are going to be two-dimensional matrices. Okay? Okay, good. So let's continue building up this thing and to finally get our ultimate goal. So I want to find the 1, 3 position. The 1, 3 position is right there. And so how do we do it? How do we multiply 1, 2, and 3? Okay? And the answer is as follows. There's two possibilities here. There's two possibilities here. One is multiply it 1 by 2, 1 times 2, and then multiply 3. And the other is multiply 1 times 2 times 3. Okay, so we have to keep an eye on these two possibilities. Okay, great. How many operations does it take to multiply this? And then we'll do this in a second. And the answer is, this is 650 plus 0 plus 455. I'll show you where I get those numbers. Okay, first thing is multiply A1 times A2. Now, there's no choice in that. We know that. That's 1, 2. So this is M1, comma 2. Okay, great. Then you have to multiply A3 times A3. 3 times A3, or just leave A3 by itself, is the 3, 3 position. This is M3, comma 3, which is 0. Okay, and then finally, you're going to have to multiply these two things. Now let's see what the matrices are. A12 is going to be a 5 by 13. A1 times A2 is going to be a 5 by 13 matrix. A3 is a 13 by 7 matrix. So 5 times 13 times 7 is equal to 455. Let's write that out. 5 times 13 times 7 is 455. So we're adding these three things. I'm just showing you what these three numbers are. And you get a grand total of 1105. Great. That could be the best way of doing things, but we have to check another way. Okay, what's the other way? Well, we can have A1 by itself. How many operations does it take to have A1 by itself? Answer, just 1. I'm sorry, just 0. You're not multiplying it, so it's 0. I'm going to write that as M1, comma 1 plus, okay, what else? Well, I want to know what's the least number of operations to multiply 2, 3? And the answer is 2, 3 is 910. This is M2, comma 3. Plus, there's pluses in between here, there's pluses in between there. Okay, plus, okay, what's the last thing? Well, I want to multiply this 5 by 10 matrix, this is the outermost multiplication, this 5 by 10 matrix by 2, 3, which is 10 by 7 matrix. 5 by 10, 10 by 7, so that's equal to 5 times 10 times 7, which, thank God I wrote it out, that's 350. Okay, great. And if you add that up, what do you get? If you add that up, what's the smallest what's smaller, this or this? And the answer is this. Okay? And so we write that down. We looked at this way, and we have to find the minimum, and we find that this is the minimum. So the 1-3 position is 1105. Okay? And what we have to say is as follows. Don't move. We're going to multiply right in front of the 3. And so in the 1-3 position, we're going to put a 3. You'll see why in a second. Okay? I just want to say, when we multiply the 1-2, well, I'm not sure about that notation. Okay, great. Good. That takes care of this box. Now we take care of this box. Ready? M 2-4. This is the 2-4 position. Okay? And we have to go through it. There's two possibilities for this. There's either A1, A2, A3, A4. We can multiply it like this. Or, that's or, A2, A3, A4. We can multiply it like this. Okay? And so let's do this. A23, we know what A23 is. That's 910. 910. A44, we know what that is. How do you get this A4 by itself? That's 0. Okay? Okay? So this is in there, this is in there. Plus, let's see what else we have. Okay, you have 2, 3 is one matrix. That's a 10 by 7 matrix. And that's a 7 by 12 matrix. So how many operations does it take to multiply a 10 by 7 matrix and a 7 by 12 matrix? And that's 10 times 7 times 12. 10 times 7 times 12 is 1750. Okay. Oops. Sorry. 10 by 7 by 12 is, is 840. Okay. And if you add 910 and 850, you get 1750. Good. Okay, let's do this a little bit quickly. You have a 3 by 4. 3, 4 is 1092. I'm sorry, so let's do this. This is 0. To multiply A2 by itself is, you're not multiplying it by it, you're just leaving it itself, so that's 0. Plus a 3A4. A 3A4, we know what a 3A4 is. That's 1092. 1092. Okay, plus, let's see what we have here. You have A2, which is a 10 by 13. And 3, 4, A3, A4 is a 13 by 12. So how many operations does it take to multiply a 10 by 13 and a 13 by 12? And the answer is 10 times 13 times 12, which is equal to 1560. Okay, now add these together and you get 2652. 2652. Okay, what's better? What's the least number of operations? 1750 or 2652? Answer 1750. So we put 1750 here. Okay, great. Okay, great. And I'm going to put a 4 here because we put the closing brackets not in front of the 3, but in front of the 4. So we're going to put a 4 here. Okay, I'll explain it in a second. You'll understand the bottom bracket in a second. Okay, great. Let's move on because we have one more box to fill, and this is the ultimate box. So let's move on and do it. Okay, and so finally let's do M1, 4. There are 3 ways to do M1, 4. One is have A1 and then A2 A3, and then A4. And I know the best way of putting in parentheses in A2 to A4 because I did that already right over there. Okay, that's one possibility. Another possibility is A1, A2, A3, A4, and that's like this. Okay, but there's a third possibility also. What's the third possibility? Or, okay, A1, A2, A3, A4, okay, and you do it like this. Okay, good. Now, the main point is, a lot of this information is already up there. So we're going to use that information that we already get. We're going to use the earlier information to find the answers to the later information, to the bigger question. Okay, so let's do this. A1 by itself is 0 operations. Let's just write that in. That's M1, comma 1 is 0. 1, comma 1 is 0. Okay, next, plus A2 to 4, 2 to 4 is 1750. So 1750, that's M2, comma 4, plus, hold on, we have to do the last multiplication. So let's do the last multiplication. A1 is a 5 by 10 matrix. A2 through A4 is a 10 by 12 matrix. How many operations does it take to multiply a 5 by 10 matrix and a 10 by 12 matrix? Answer, that is 5 times 10 times 5 by 10 and 10 by 12. And 12. And that altogether is equal to 600. 5 times 10 is 50, times 12 is 600. Okay. If you add these numbers together, you get 2,350. Okay? Now, we know what the best way of doing this 3 is. We did it already. We did it here and we recorded our results over here. Good. Let's do this. There's another possibility. There's 3 possibilities for this one. Okay? And this possibility is as follows. Okay? A1, A2 is 650. A3, A4, 4 is 1092. Okay? And now we have to multiply these 2 matrices out. Here's one matrix, here's another matrix. How much operations does it take to multiply these out? So this is going to be a 5 by 13. A1, A2 is going to be a 5 by 13 matrix. A3, A4 is going to be a 13 by 12 matrix. Okay, how much operations does it take to multiply a 5 by 13 and a 13 by 12? And the answer is 5 times 13 times 12, which is 780. Okay, and if you add these all up, you get, don't move, 252522. Great. Okay, let's do the last possibility. Notice this is better than this. We're definitely not going to do this one. This is better than this, but maybe this is better. Let's see. Let's go through it. Okay, great. How many operations does it get to multiply this? Well, A1 through 3 we did already. That's 1105 plus A4 by itself is 0. You're not doing any operations to get this by itself. Plus, okay, plus what's left? I got to multiply this guy times this guy. Okay, this guy is a 1 from A1 through A3. A1 times A2, A times A3 is a 5 by 7 matrix. This is a 7 by 12 matrix. A4 is a 7 by 12. So 5 by 7 matrix times a 7 by 12 matrix is 5 times 7 times 12, which is equal to 420. Okay, combine that together and you get 1525. Okay, conclusion, this is your best. Okay, so question, how many operations do you have to do? You have to do 1525. Okay, great. And what do you put over here? Where is the operation over there? it's you close the outermost operation is closed before 4, so you do that. Okay, great. Okay, so the best way of multiplying is going to be A1, A2, A3, A4. Okay, and the outermost operation tells you do 4 by itself. Great. I didn't need those last parentheses, but that's fine. Let's leave the parentheses in. Great. Now, what's the best way of multiplying A1 through 3? Answer: from 1 to 3, the best way is to do it like that. Okay? And why? Because that 3 is right before the end. So if you want, you can put parentheses around that. Anyways, that is the best way of multiplying these 4 operations. Okay? So that's a nice little algorithm. Okay? And we have to ask how many operations, so how much work is done. Well, let's go through the algorithm in a second. Okay, great. So that takes care of that. So the best possibility is that. By the way, what's the worst? Well, I'm not sure what the worst is, because that's the worst if over here, but you could have gotten much worse than that. So 2522, I suspect that worse than this is what we saw before, something with the 2652. That would be even worse. Okay, I erased it so we can't see it, but that would be even worse. Great. Let's just go through what we did here. We filled this matrix from the bottom up, and I'll show you what that means. We filled this matrix from the bottom up, and we got the last thing. And how did we fill this matrix? We tried all possibilities. And now we have to be a little bit formal about what that means. This tells you how many operations. This tells you where to do the last operation. Okay, good. Okay, now that we did an example, I want to show you the algorithm. And the algorithm is as follows. You have to multiply A1 through AJ. Okay? And assuming you have all the previous information, I just want to show you what each single thing is. Well, here's the question. How shall you parenthesize the last thing? Well, here's a couple of possibilities. One is, do it like this, with this by itself. That's one possibility. Here's another possibility. Okay? Do these two parenthesized, and then do this one parenthesized. Here's another possibility. Do these 3 parenthesized, and do that like that. Okay? Now here's another possibility. Do the first 4 parenthesized, and then do the rest. Okay? And then you keep on going. Dot, dot, dot. Okay? The last possibility is do all till j minus 1, and then multiply that. You have to try all these different possibilities. Okay, now, question. What's the shortest to do this one? Well, you have that already listed in your matrix. This one, you know, is 0 operations, but then you have to bring them together. How about this case? Well, you have these, how easy it is to multiply these in, and now you have this in your matrix, and you do that. Same thing here. You have how to multiply AI plus 1, AI plus 2 in your matrix, okay, and you have how to multiply, what's the easiest way of multiplying A3 through AJ over here. So this would be A3 through AJ over there. Okay, you have all this previous information, and what you have to do in order to get the last information, in other words, which one to do, is as follows. So what you're looking for is as follows. Mij. How do you multiply the I for all the matrices from AI to AJ? Answer. It's the minimum, the smallest, okay, of the following. I is less than K, which is less than J. One of them is equal. Okay, this is less than or equal. This is less than not equal to. You have to look at the minimal where K is somewhere in between. Just like this, K, where you're cutting it off, is somewhere in between. Okay, K is one of these things. Okay, so you give an I, you're given J, and so the I and J are fixed, but the K has to be somewhere in between. And what are you minimizing? Well, I want to know how many operations does it take to get from I till K. Okay, the first part from I. So let's just do the general case. The general case is this is AI till, oops, AK. Might have to be a, and then this is AK plus 1 all the way down, all the way till AJ. Okay, so MIK plus MK plus 1, that's this guy, till till M till J, plus, okay, now we have to worry about the dimensions. Okay, I have from here to here, I have from here to there, but now I have to know how to multiply these things. The dimensions are given in the book. They're given as, if you have n numbers, you need n minus 1 or n plus 1 dimensions. But here's the way the book does it. P of I minus 1, that's the dimension, that's number of rows of AI, times, you have to do the number of columns in AK. Number of columns in AK is P of K. Okay, and finally, you're going to have to do this one, and that's going to be times A of J. Okay. So what you have to do is you have to go through all possibilities of this, see how much it is to get the first matrix, the left side, see how much it is to get the right matrix, these pieces of information you had before, and this is, you multiply the correct dimensions like that. Great. Okay, let me just tell you what that S matrix that we ignored mostly. S matrix is, hold on, let me just show you. Basically it's as follows. Yeah, I shouldn't have done it like that. Okay, so let me just show you. It's as follows. If S of I comma J is equal to K, that means where to do the blocking, where to block them off. That means the best answer is from AI till AK minus 1. Okay, that's going to be a thing, and this is going to be A of K till A of J. Okay, so it's equal to the number of, okay, that means you stop right there. So it preserves, you find what the minimum is, and then this tells you how you get the minimum. So that's very nice. Okay, and that explains it. I just want to spend 3 minutes, not even, going through the algorithm. I want to write up the algorithm. Okay, so I just want to go through the algorithm of how it's done, because it's a little bit strange how we fill this matrix. Okay, again, dynamical programming is all about filling a matrix. But usually when you fill a matrix, you have m rows, n columns, you start at the top row and you fill it out one by one, etc., etc. For every row, and then you do every column, you have a loop within a loop. But here we're not. We're filling it basically along the diagonal first. Okay, and so it's a little bit different, and I'd like to show you. You have to read the algorithm on your own. I'm not doing every single part. It's on page 375. I'm skipping some parts that are on top, but you can read it on your own. But I'm just helping you go through it and see what it is. It says as follows: for L is equal to 2 to n. Okay, so first of all, I filled in the one part. I'm sorry, L is going to be how long from AI till what? How long will how many matrices do you want to fill? Okay, so let's go through it. From 1 to 1, that takes 0 operations. From 2 to 2, that takes 0 operations. So that's filled in before. But now we have to do from 1 to 2, that's of length 2, or from 2 to 3, or from 3 to 4, or from 4 to 5. Those are 2 things, 2 matrices. Okay, and we do that. So for L is equal to 2 to n, that's the length of how many matrices you're going to multiply. Okay, great. Now we have as follows. For I is equal to 1 to n minus L plus 1. So this tells you what the ith place is. So start at 1, that's 1 over here, okay? And this is going to tell you how far it is. So, and go till n, but stop a little earlier because you're not going to have all the way. So let's just do the first one. You're going to do 1, 2, you're going to do 2, 3, you're going to be 3, 4, you're going to do 4 and 5. So, okay, good. Okay, now let me tell you how to get j. J is the last one from your length of two things. So j is equal to I plus the length minus 1. Okay, so if L is equal to 2, so it's going to be I plus 2 minus 1, which is 1. So the first time you're doing 1, 2 position. Let's just do the next time. L is going to equal to 3, so you're going to go from 1 to 3, 2 to 4, 3 to 5. Okay, the last one you're going to have L is going to equal to 5. By the way, the example we did was a 4 matrices. I'm doing here 5. The book does 6 matrices. Okay, so you can see it even more clearly. So from 1 to 5, so L is going to equal to 5. So look what it is. I is going to start off as 1 till 5 minus 5 plus 1. 5 minus 5 is 0 plus 1 from, so that's going to equal from 1 to 1. Okay, good. So we're only going to do the 1, the last one. J is going to equal to 1 plus 5 minus 1. 1 plus 5 is 6 minus 1 is 5. So this is the 1, 5 position. Okay, so I'm just showing you, these 3 lines show you how to fill a matrix from the diagonal till the corner. Okay, great. Okay, so first thing is we're looking for a minimum. So the way you look for a minimum is as follows. You set up such that the maximum. So let's say you're looking for the youngest person in the room. You start off with youngest so far is equal to infinity. Okay, and then you check everyone to see if they're less than youngest so far. So that's youngest so far. So the smallest we have starts off as infinite. That's for surely going to change because we're going to have less. Okay, and goes as follows. For k is equal to I to j minus 1. This is what I said, that between I and j, you're going to have a k. And you're going to try all possibilities for k. Okay, and here's what you do. Q, that's the number of operations, is going to be how many operations does it take to multiply the ith matrix all the way to the kth matrix, plus how many operations does it take to do the k plus 1th matrix to the jth matrix, plus don't forget to do the final bringing together of these 2 outermost matrices, and those are the things. Finally, we say as follows. We're looking for the smallest one. So if Q is less than what was previous the best, okay, we'll say min so far, and then Mij is equal to Q. Make this the new minimum. Sij is equal to K. Okay, and you go through all K in order to do this. Each one you calculated, each one you compare. If you have to change, you change. At the end, you return the M matrix and this S matrix. Okay, so that takes care of that. Question, how much work is done? How much work is done? And the answer is, look, you have an n squared matrix. You have an n squared matrix. Okay, but you don't have to fill in the entire n squared matrix because this half of the n squared matrix doesn't make sense, because this is when j is greater than I. That doesn't make sense. So it's basically, you have to fill in n squared over 2 of these boxes. And for each one of them, you pretty much have to multiply times, in the worst case, n. So it's about n to the third. It's about n to the third. Okay. Now, question. Maybe that's a big waste of time, n to the third. Okay. Maybe that's a big waste of time. Answer. We saw the Catalan numbers. What's another way of finding out what's the best way of multiplying these matrices? Try every single possibility. But we saw with the Catalan numbers, remember you had 2n over n divided by 2n choose n. How was it? 2n choose n over n plus 1. Okay. Well, that's exponentially large. That's exponentially large. You don't want to try every single possibility. You don't want to try all brute force possibilities. You want to do this nice polynomial. It's about n to the third. It's a little bit less than n to the third algorithm, and it's a very nice thing. Again, it's n squared over 2 boxes that you have to fill, and for each one of them, you have to do this little loop to calculate what's the min of all of them. Okay, so that's very nice. So that's our first real example of dynamical programming. In the next class, we'll do 2 other examples of dynamical programming, and then we'll be world-class experts in dynamical programming. Take care.